Welcome everyone. We're so excited to be here at the 2025 Brian Pitt Excellence Award final. We've got all our finalists today with us, the jury, so thank you for being here and we really hope you enjoy the session. I'm Emma Vizzino, a rotating equipment engineer working for RWE, and today I will be chairing the session. I'm also part of the Young Engineers Committee of the ETN. So, first of all, I just wanted to say thank you to everyone that has made the Brian Pitt Excellence Award possible and everyone that's worked on it over the last 6 months. Thank you to the steering committee, Alberto, Antonio, Erica, Giuseppe, and for our jury team being here and everyone that has applied and engaged with our process. The Brian Pitt Excellence Award is here to showcase the innovative research ideas of master students in the field of energy efficiency and low carbon solutions in turbomachinery, but also to promote knowledge exchange and recognize those outstanding contributions in the field. I am here today with our 5 finalists. You have done so well so far to get here, and I can only wish you a lot of luck for today. I'm here with Krzysztof, Franco, Thomas, John, and Mohammed. And what's the prize? We'll have one winner by the end of the session. And the prize for them is to have a fully funded participation to the IGTC 2025 with the possibility to present a paper, to be an invited paper. But also our finalists are not being left out. They have a discounted entrance fee to the conference, but also the possibility to present their work with a poster. So I think some exciting things to look forward to. I'm here also with the jury. Thank you very much for being here today. I'm here with Dr. Andrea Ciani, Hydrogen Technology Manager at Ansaldo Energia, with Dr. Rainer Kurz, ETN Emeritus Member, ex-Solar Turbines, with Daniel Phillips from SSC, working as a rotating equipment engineer, and Alberto Patti, a PhD candidate from the University of Genoa, but also part of the YEC ETN. So brilliant. Before we start, I'd like you to pass it over to Giuseppe for a few words from ETN.
So on behalf of ETN, welcome everyone. I'm very pleased to have you all finalist jury and also attendees at this Brian Pitt Excellence Award final. So clearly I'm not Krzysztof. Krzysztof couldn't be here today. So my name is Giuseppe Tilocca. I'm technical lead at ETN Global. And it's a great pleasure for the ETN Secretariat to support this event, but also support young talent in the turbomachinery and the energy community. Very clearly, we need young talent. So the energy transition is a very difficult, uncertain path that cannot be done without the right people, without building from now the new energy leaders. So I must say, I had the pleasure to read some of the papers that were received. And honestly, the quality of the selected work this year has been truly outstanding. So and we are excited to see it presented today. Of course, summarizing an entire master's thesis in just 7 minutes is not an easy task, it's a challenge, but that's why it's a competition, that's why it's a final. So I like to wish all of our presenters the best luck. This is indeed a final, but also a great way to explore the latest research. So as ETN, in the name of the community, we are looking forward to this great session. So good luck to everyone.
Brilliant. So as we have a packed agenda, our finalists have 7 minutes to present, 5 minutes of question and answers, and then our jury has 15 minutes to get us a winner. Over the time, they will go out to a room and we will have a special guest here to just talk about career development and her journey. So, wishing again good luck. I want to pass it over to Thomas Hollweck from the University of Munich. The screen is yours and over to you.
Good afternoon, everyone. Hope you can hear me. I'm Thomas Hollweck, and I'm very happy to present my latest research in the field of thermoacoustics to you. which was on a three-dimensional Helmholtz solver coupled with data assimilation techniques. I conducted this research at the University of Cambridge as part of a collaborative research project with Rolls-Royce Deutschland, and I was finally able to apply the methods in this work to a real test rig of Rolls-Royce. So the motivation of this work are thermoacoustic instabilities. Thermoacoustic instabilities correspond to large pressure amplitude oscillations, which can destroy any combustion system. In this case, we see a gas turbine, which was destroyed by thermoacoustic instabilities. These instabilities also lower efficiency and prohibit us from operating at some operating conditions, and are a major channel in lean premixed combustion and also now for hydrogen. How do they involve? In a combustion chamber, the flame acts as a source of sound and emits acoustic waves, which can be then back reflected and propagate back to the flame, such that the feedback loop is closed. And in this feedback loop, we can excite those instabilities if the pressure perturbations and the heat release fluctuations are in phase, leading to high amplitude limit cycles potentially. However, we have the possibility to apply small design changes to mitigate those instabilities, since the thermoacoustic feedback loop is very sensitive to any kind of model parameters. However, to predict those changes, we need a quantitatively correct model, and just a qualitatively correct model is therefore not sufficient. And there are several models employed in thermoacoustics which differ in their model assumptions, their complexity. The one we focus on is a Helmholtz solver. A Helmholtz solver solves the 3D acoustic wave equations based on partial differential equations, and has, however, some simplifications like the assumption of zero mean flow, meaning it has some systematic model error. However, it is computationally efficient enough to perform some shape analysis, shape optimization in the early design process of a combustion chamber. In this work, we therefore investigate whether we can make such a Helmholtz solver, which is kind of quantitatively correct, even more qualitatively correct, even more qualitatively accurate by incorporating some acoustic damping due to mean flow, which is inherently neglected. And then in the second step, and this is what I focus on today, use data assimilation techniques to learn from data and possibly yielding a quantitatively accurate model, which is required. And we finally applied these methods to the Rolls-Royce Scarlet rig depicted here, which is kind of a state-of-the-art benchmark aero engine test rig. So how do we learn these parameters? We have a physics-based model with a bunch of parameters which we are very uncertain of. And we use Adjoint-accelerated Bayesian inference to get a posterior probability distribution of these parameters, incorporating all the prior assumptions we have on these parameters, and then this is formulated in the likelihood term, finding those parameters who agree with the prior and also explain the data very well. And this process is illustrated here. So when we assimilate pressure measurements, we learn the values of those parameters and, as we see in the Gaussian here, get more certain in them. And to make it computationally feasible, we use adjoint methods. So the computational effort does not scale with a number of parameters. Let us apply this to this test rig, which is depicted here. So the Scarlet test rig is operated under realistic engine conditions. And the combustion section in the middle is surrounded by two ducts, where we have some microphone installed, where we then can deduce pressure measurements, and we can force this rig upstream and downstream. This combustion chamber has a lot of complicated flow features, which a Helmholtz solver cannot model, but we include physics-based models in order to resolve this. And therefore, we have three-dimensional simulations with this Helmholtz solver, and in addition, these physics-based models, and assimilate data from upstream forcing and downstream forcing to get now a quantitatively correct model. So let me show this in the real data. So we consider 20 frequencies at 10 microphones, which are 5 upstream and 5 downstream. And before assimilating the data, we see our model is super inaccurate, and we are also very uncertain about the model prediction. However, the model is depicted in blue with uncertainty bounds also in blue. Experimental data of pressure and amplitude and phase are in red. And we see how efficiently we can learn from this data by only assimilating a few parameters. We basically capture all the qualitative trends and also achieve high quantitative accuracy in a wide spectrum of frequencies. Only here, for example, in the low frequency regime, we see we have to do some additional physics-based models to account for. The same we can do for downstream forcing, where we see that the data assimilation yields a huge increase in quantitative accuracy, even though we just use a Helmholtz solver with 4 parameters in this study. Let me summarize. This study has shown that we can use a very simple model, a Helmholtz solver, leave the physics in the model, use data assimilation techniques with adjoint-accelerated Bayesian inference, and then get a way more quantitative, accurate model. We can use such a model, for example, in the early design process of a combustion chamber to more reliably predict shape optimizations, and also go to frequencies where we don't have measurement data with uncertainty. In future research, we might extend the study even to reactive conditions and extrapolate to various operating conditions to verify our study. Thank you very much. I'm looking forward to questions.
Thomas, brilliant timekeeping there, even before the 7 minutes. Also, a super interesting presentation. Thank you very much. Jury, I would like to invite you now to ask questions, if possible. We have about 5 minutes per candidate, just as a reminder, so please. Yeah, of course, Andrea, please.
So hi, Thomas. Really nice presentation. And actually, I had 2 questions that go possibly together. One is about the frequency range that you explored. I think you said it's 10 or 20 frequencies that you covered. And I was wondering if you chose these 20 frequencies based on something or they are homogeneously distributed. And also whether the model is better capable to capture some frequencies than the other. Like you were mentioning something on the low frequency, if you could expand on this. And also I was wondering if you, why did you want to, you already start straight away with flame scenes. So as I understand, this was done in a non-reactive environment.
Okay, very good questions. I like to start with the first one. So here we have non-dimensionalized frequencies for sake of disclosure. So, but I can roughly tell you that the frequency range is somewhere up to 1100 Hertz. And the frequency data is from Rolls-Royce, and these are kind of the frequencies which they found meaningful. Particularly in this region, they found we have a spectral peak, as we see. Therefore, we have more data gathered here. And I basically used all the data available in this case. And maybe a comment on this. We see we have some acoustic damping in the low frequency regime, which might not be modeled. So we have to have even more sophisticated physics-based models. And also in the Helmholtz solver, we have some phase error, which might occur in the high frequency regime, which is, however, for example, observably here, is, however, captured pretty well. To the second question, in thermoacoustics, we always start with a cold model, as we don't have the uncertainty of the flame. Then we try to make the cold model correct. And then, for example, in a second stage, when we learned all those parameters, use our model to, for example, infer flame behavior in the hot rig. So if we don't manage to describe the cold rig, we should not even try the hot rig in this case.
Okay, nice. Very good. Thank you.
I don't know, am I the only one who has the hand up?
Yes, please, Rainer, it's over to you. Thank you.
Thank you. Well, it's actually a really interesting study, in particular because the industry really was plagued for a while with combustion instabilities. Now, would you have to get the input data each time you change the operating conditions of your engine and therefore your combustor, because you run from full load to part load, or you operate at different ambient conditions?
That's also a very good question. In the study conducted here, I have a set of operating conditions given by, as stated here. However, the idea is, because we have a physics-based model, this physics-based model accounts for the operating conditions. And therefore, if it's a good model, and we try to judge whether it's a good model by this investigation, it should extrapolate to also non-measured operating conditions, which is definitely a part of future research and one of the most or biggest advantages of a model, because the experiments are super expensive for particularly the hot experiments.
Thank you.
Brilliant. Thank you for the question and answers. We have 1 minute left. Anything urgent? I think all is clear. Perfect. Thomas, thank you again so much. I can now relax. And I would like to pass it on over to Franco Agustin Rizzi from Politecnico di Torino. Good luck to you. And the 7 minutes start now.
Good afternoon. I'm presenting the key findings of my master thesis at Politecnico di Torino in contribution with the team member Ethos Energy. Is the CFD analysis of a lean premixed gas turbine combustor for hydrogen applications. Ethos Energy studied an injector that allows the introduction of hydrogen and methane mixture into a 5 megawatts previously gas turbine, with the idea to reduce carbon and NOx emissions. This comes from the general tendency of having natural gas as one of the main energy sources in Europe. So this is we can say that the infrastructure is gas-based, and in the short term, this would allow to reduce significantly the emissions in the short term, actually. So a CFD model, a RANS model, is developed in order to study it and be sure that the combustion will work and how it will work, and to study it and to characterize it. And here on the right, you can see this is the combustion chamber, and on the left is the model of the injector. Taking advantage of the axis symmetry, it's reduced to a portion, and the injector it's separated into 2 different models to reduce again the model here. And then the profile is extracted, of the fluid profile is extracted here and here, and in order to put it back to copy it towards the combustion chamber. But of course, this has to be reconstructed and to then be able to be set up in the simulation. And then the question arises, why do all this? Why not model the complete model with the injector without coupling this and making this complication? And the reason is this: there's a 70% reduction in the number of elements, making it much more feasible for its reproduction and have a lower computational requirements. This swirl, this reconstruction, it's important to be done correctly. And here we have a model where this swirl was not considered, and here one where it is. And what you can see is that in the inlet, being normal to the surface over here, the fluid just goes from the inlet to the outlet without any mixing, while on the other case, you have some vortices generated and breakup, which it's coherent with the swirl number that characterizes the swirling movement, and it's higher than 5. When it's higher than 5, has great recirculation, and also generates a low velocity region over here, allowing for the flame to be anchored. We can looking into the mixture fraction and the static temperature maps, we can see that it becomes way more uniform with the actual mixing, which makes sense. You may note that here there's a difference between this part, and this is the modeling of the effusion holes. This is the cooling of the wall of the liner, and these are the dilution holes. These are the diffusion holes. These are the splash holes. And one first approach was to use 2 cooling stripes for the fluid coming through these small holes. Meshing it would be quite expensive in terms of an element size. And an alternative was found to be used a perforated wall model that assigns to surfaces fluids to be injected. And this requires an extraction surface So the annulus had to be incorporated into the model. And these four surfaces are the injection side of the effusion holes. Note that the dilution holes and the splash holes are also included inside the annulus, allowing it to be modeled as well. So it was a double improvement. Looking into the two cases, first with the two stripes, there wasn't a great cooling film, so it's become more realistic. And then as the dilution holes were included, the original case was being normal to the surface, and this was not the actual case. Once it's modeled, it has a bit of deviation. Changing the inlet and the cooling changes the outlet temperature distribution, that is the temperature over here. And it becomes way more uniform, and this is the desired result. And you can see also here some low temperature regions. And to characterize first the uniform of the dimorphicity of the outlet, the parent factor is computed for the several fuel blends. And the parent factor is quite low, and this is desired in order to have a low NOx afterwards. Still, there is a slight increase, but it's not that much, so it's acceptable. Then this plot on the right is generated by slicing in the radii and averaging the temperature. And two things are noticed. First, the low temperatures in the top and the bottom. These are desired in order to preserve the vanes of the turbine that comes afterwards, after the combustion chamber. And then that the peak temperature occurs a bit above the mid-height of the vane, two things that are desired when designing combustion chambers. Then, in order to look at the flame, we looked into a transient species, that is the OH in this case, and taking this line where the mass fraction of OH becomes its highest, we use it as a measure to see how it moves upstream towards the injector as the hydrogen in the fuel is increased. The other thing that can be noticed is that the flame becomes more compact in all the cases and thinner. These things are expected from the theory, so we can say it validates the model from the combustion. So to sum up, the achieved first was the 70% reduction in the number of elements, this making it way more feasible for reproduction, for doing it, for reducing computational requirements. Then achieving an accurate combustion model is required in order to compute the NOx simulation afterwards, because it's a post-process of the combustion. And then the 4 different fuel blends were achieved, saying we can characterize a bit the combustion chamber. Thank you very much. I'm open for questions.
Brilliant. Thank you, Franco. Perfect timekeeping there as well. A very interesting presentation. Jury, over to you for the questions. Yes.
Yes, Andrea.
Thank you.
So hi Franco. Thanks for this nice presentation. I was wondering, as I understand you explored the range 0-50% hydrogen.
Yes.
Whether you are planning to go for the full way until 100% or larger shares of hydrogen, why you limited the work there. And I was also wondering, maybe I missed the pressure at which you are conducting the study.
For the hydrogen amount, we are aiming at 60%, the limit, and being this for stability of the flame. And for the pressure, I can show the pressure losses of the combustion, which were when increased the hydrogen became a bit lower, but not significantly. The actual numbers I cannot disclose.
Okay, yeah, thanks. But it's not atmospheric pressure, so it's an engine pressure.
Yes, it's exactly.
Okay, yeah, thank you.
Perfect, thank you. Rainer, over to you. Sorry, we cannot hear you. I think, yeah.
Okay, now.
Perfect. Yes, perfect, thank you.
So this is a really interesting study. I was just wondering, how did you model your upstream boundary? Meaning, did you model the potential dynamic behavior of your injectors? For example, would you have been able to detect flashback into the injector in your model?
Well, actual flashback was not the idea of looking into the upstream movement was looking into the position of the highest point, the highest concentration of OH. This is how we saw the flame moving upstream, but actual flashback we were not we didn't see actually.
Okay, but you would have seen it if there were flashbacks. So the model would have been capable.
Exactly.
Okay.
Exactly. And there were, I believe that a model without there were some models that before setting up the settings that saw something going towards injector, but we would be able to see it. Yes.
Okay, thank you.
Perfect. Thank you. Yes, we've got a question from Mohammed. Yeah.
Yes.
I think he's got problems with this microphone. Try again, please.
Yeah, I got access now.
Perfect, thank you.
Yeah, very interesting presentation. I have just a quick question regarding to the nozzle diameter. So what was the diameter of your injector?
Sorry, the
diameter of your injector.
And no, I can't say the diameter of the injector because I'm not allowed. So, sorry.
Okay, no problem. Yeah. Okay. Thank you.
I'm sorry.
It's okay. Intellectual property, we know. Okay. Anything else around? Any other questions? If not, Franco, you can also now relax. Thank you very much for being clear and everything and for answering the questions. I will pass it over now to Mohammed Atif Qazi from the University of Alberta. Good luck to you, and your 7 minutes start now.
Good afternoon, everyone. I am Mohammed Atif Qazi, graduate student at University of Alberta, Canada. And today I will be presenting on the topic dispersoid strengthened high entropy alloy coatings for hydrogen embrittlement resistance developed via thermal spraying. So there are increasing efforts to decarbonize energy systems. And when we talk about decarbonizing, hydrogen comes up as a solution to those efforts. According to the Net Zero by 2050 report, hydrogen is to power 13% of global energy needs. For that, there is a need to build a reliable hydrogen production, transport, storage, and conversion systems. But these systems, which include pipelines, turbines, storage tanks, to name a few, faces the problem of hydrogen embrittlement, solid particle erosion, corrosion, and stress cracking, to name a few. To combat these problems, we need to come up with a material solution, and high entropy alloys are one such material which are produced by equiatomic or near equiatomic mixing of 5 or more elements. High entropy alloys lie somewhere at the top right of the HB plot, somewhere here, so which means they have high fracture toughness with high yield strength. Overall, high entropy alloys have excellent thermal stability, outstanding mechanical properties, high hardness and wear resistances, and excellent corrosion and oxidation resistance. To protect the energy systems using high entropy alloys, we need a coating fabrication process. Flame spray is one such cost-effective process. Our group has been working on flame spraying high entropy alloys, and we have found that they have high hardness, promising oxidation resistance, high wear resistance, and high corrosion resistance. Coming to the motivation behind this study, so flame sprayed AlCO-CrFeMO high entropy alloy was developed at our group, and it has shown excellent performance against wear, erosion, and chloride induced corrosion. Zirconium comes in as a strategic addition because it forms hard Lewis phases and ZrO2. It also facilitates hydride formation and hydrogen trapping. Overall, this study investigates how zirconium addition can unlock new frontiers in flame-sprayed high-entropy alloy coating performance by integrating wear, corrosion, and hydrogen resistance into a single coating system, overall producing a multifunctional coating with the potential to combine bond and top coat functions for simpler turbine hardware protection. The objectives of the study include the development of ALCO-CRFE-MO coatings via flame spray, evaluation of mechanical performance under impact-dominated loading conditions, assessment of corrosion behavior, and finally, the investigation of hydrogen embrittlement resistance. The experimental methods include preparation of the feedstock by tumble mixing of ZR in 5, 10, and 15 weight percentage to ALCO-CRFE-MO, characterization of the powder. Then we move to the coating fabrication using flame spray on 316 stainless steel substrates, characterization of the coatings. Then the coating performance assessment using mechanical tests like micro hardness test, coating adhesion testing, solid particle erosion testing, and then the electrochemical test like electrochemical corrosion testing, Devon and Stachowski hydrogen permeation testing. The XRD analysis of the powder shows a BCC phase and a HCP, ZR-induced HCP phase. The SEM analysis of the powder shows regular and spherical morphology with average particle size ranging from 38 to 42 microns. Here is the XRD analysis of the coatings, which shows 4 phases, namely BCC, intermetallic phases, FCC phase, and spinel oxides. So as the zirconium percentage in the coating increases, the BCC phase decreases, and the ZrO2 content increases in the coatings. The SEM microstructure of the coating shows splat-based morphology with the coating thickness around 450 microns. Moving to the micro hardness evaluation, which shows an increase in the hardness with the increase in ZR reaching up to around 900 HV of hardness. Next, we have the coating adhesion strength test, which shows a cohesive failure mode with an initial drop in the adhesion strength at 5 weight percentage, but then an increase in the strength up to 15 weight percentage. The solid particle erosion testing done at 30-degree impact angle showed decreasing erosion rate up until ZR 10 weight percentage, and then a slight increase at 15 weight percentage. Comparing the erosion rate with the hardness, we see the erosion rate decreases with the increase in the hardness up until ZR 10 weight percentage, but then an increase in the erosion rate with the increase in hardness. So it shows that toughness also plays an important role in determining the erosion. Similar results were observed when solid particle erosion testing was done at 90-degree impact angle. Next up, we have the electrochemical corrosion testing, which shows increase in the corrosion resistance as the ZR content in the coating increases because of the formation of stable Al2, O3, and ZrO2 phases. And finally, the hydrogen permeation performance assessment of the coating showed initial hydrogen ingress due to high diffusion coefficient, but suppresses the hydrogen movement within the microstructure because of high trap density and low solubility, overall outperforming the substrate SS316. Coming to the conclusion from the study, so we were able to fabricate ALCO-CRFE-MO coatings using flame spray. We saw an improvement in the mechanical performance with the HEA15 ZR exhibiting the highest micro hardness and adhesion strength. HEA10 ZR is the most erosion resistant composition. ZR addition enhanced corrosion resistance with HEA15 ZR showing the lowest corrosion rate. And then HEA15 ZR is an effective hydrogen barrier. Overall, lastly, by addressing key surface degradation modes, these coatings pave the way for a resilient and hydrogen compatible turbine components. In the end, I would like to thank my supervisor, Dr. Andre McDonald, and you can connect with me and my group using by scanning the barcodes. Thank you.
Thank you very much, Mohammed. Very good presentation. Jury, I would like to open the floor for your questions.
Hi, Mohammed. Hopefully you can hear me okay there. Sorry, Ryan, for jumping in there. Good presentation. It was certainly interesting to hear that you mentioned that there was no base coat required for this. Did I hear that correctly? And then you tested it on a particular grade of stainless steel. But has that been proven to be a successful and appropriate coating method consistently? And also, have you tried using this coating on different grades of stainless steel, perhaps other materials as well, other metals?
I think you asked about the SS316, right?
That's right. Yep, that's what you seem to have used as your base material for this.
Yeah. So, like the substrate for our coatings was SS316, and we did our testings on SS316, and then the different coatings with the ZR in it, the zirconium in it. So overall, like on all the testing that we performed, the coatings outperformed the base material SS316. And to answer the second part of your question, like we only did the testing on 316 and no other grade of steel.
Okay, thank you. Thank you, Mohammed.
Yeah.
Thank you, Rainer. Over to you.
Yeah, this is very interesting research. I was wondering though, where in the engine would you actually use this coating? Would that be on the turbine blades and nozzles?
Yeah. So like definitely on the turbine blades and nozzles, and like we are also looking into how to, like if there is an internal cylinder, to how can we coat on the internal surfaces of cylinders and stuff like that. So for now, like it will be repair coatings on the turbine blades and the nozzles.
Okay, if that's the case, did you look in any way, shape, or form into the spalling resistance of that coating?
No, nothing on that.
Okay, thank you.
Thank you, Alberto.
Yeah, thank you for this interesting presentation. I would like to ask you, based on the cost and integration, which is the solution that it's the easiest solution to be integrated, the most feasible at the moment? What do you see as the easiest solution?
Easy, like in the coating fabrication process, or?
Yes, for coating fabrication and integration in we can say in an existing machine, something that at the moment can be integrated more easily, we can say.
I think like flame spray is one of them, because it is quite out there in the industry. It is being used quite a lot. Next, I think cold spraying is another process that is a lot of work is currently being done on cold spray. So that can also come up in the future as a potential, like cost-effective method for the repair and maintenance coatings.
Thank you.
Perfect. Thank you, Jury. Thank you, Mohammed. Can now relax. Thank you for your presentation. And I would like now to pass it over to Jean Bériot from the University of Mons. Good luck. And the 7 minutes start now.
Okay, thank you. Okay, so looking for. Okay. Do you see it?
Yes, all okay.
Yeah. Okay, perfect. So blackouts, uncomfortable, isn't it? This shouldn't be the price to pay for having a decarbonized electricity. Indeed, renewable energies, while emitting no CO2, induce a crucial lack of flexibility, reliability, and dispatchability. But hopefully, there still exist solutions to cover this lack while producing 100% decarbonized electricity. Among these, CCS-enhanced gas turbines on one side with many linked projects, Northern Lights, TCM, etc. And on the other side, hydrogen-based gas turbines with also plenty of interesting contributions, Flex for H2, H2 med, and so on. But even if it seems to be technically feasible, is it economically viable? And what's the best solution? In this context, one of the main actual needs of ETN is to determine which of the two technologies will be economically more viable by uncovering the economic tipping point between the two. And this is what I did in this study by first performing a techno-economic comparison of the technologies in their combined cycle form, and then implementing an application allowing industry members to get their own results with their own parameters. And I did this by first gathering technical data, allowing me to implement a model on Aspen economics to get technical and economic values that I later cross-validated with data from industry and literature, ensuring the implementation of a consistent economic model of the two solutions to finally get results. So let's begin with the technical part of it by first talking to you about carbon capture. The main economic advantage of this is a reduction of the carbon taxes, but this is at the expense of some negative outcomes. Indeed, this process will lower the efficiency of your power plants, and then it is an expensive process with particularly high investment cost and also involving additional OPEX, but we will see these later. Now, what about hydrogen gas turbines? Even if burning hydrogen has a significant advantage of emitting no CO2, there are still some negative impacts, which are notably the efficiency reduction of the CCGT, because 100% hydrogen capability is currently only possible for aeroderivative gas turbines with wet or dry low emissions burners. And then you also have a price increase of the CCGT directly linked with the increased complexity of hydrogen gas turbines. Okay, to end up this technical comparison, we can compare the combined cycle efficiencies of the different base cases considered. And this results in a basic statement. Reducing CO2 emissions also reduces the net efficiency of the CCGTs, with hydrogen CCGT having the lowest efficiency. However, even if hydrogen gas turbines currently have bad efficiencies, their potential is high and it is possible to get efficiencies comparable to simple CCGT in the near future. But what's the price of these power plants? Well, this can be plotted on this chart, where you can see that carbon capture is expensive. And by expensive, I mean twice as expensive as a hydrogen gas turbine. Indeed, while investing in a hydrogen CCGT will only be 25% more expensive, capturing 100% of the CO2 will lead to 150% more capex. And then, what will be the cost to run each of these power plants? And this can be plotted the same way. And what you can first see is that ETS, here in yellow, has a high influence on the marginal cost of a simple CCGT, while implementing carbon capture will be more impacted by the CO2 transport and storage cost, here in red, which seems non-negligible. And then another hidden factor, which is the increase in fuel costs due to an efficiency decrease of the CCGTs. On the other side, for hydrogen gas turbine, the efficiency penalty impact is directly combined with a fuel price increase due to the high price of hydrogen. And now let's see the impact of it on the results. And let me first compare the LCOE of the different technologies, where you can see that a CCS doesn't increase the LCOE of a CCGT that much, with an increase mainly due to the additional capex, while a hydrogen CCGT LCOE will be more than 10 times higher due to the higher marginal cost. But what about the tipping point between the technologies? And without any surprise, there is an economic tipping point after 15 years. But my question is, do we really care about this tipping point? No, the main conclusion is any of the two solutions is currently worth it. But hydrogen-based CCGT has more work to do than CCS-enhanced CCGT to be economically viable. Knowing this, what I can tell you is that ensuring hydrogen prices averaging 2 euros per kilogram is crucial before deploying hydrogen-based CCGTs. And this represents a 45% reduction for blue hydrogen prices and a 75% reduction for green hydrogen prices. And then For CCS-enhanced CCGTs, a long-run important challenge would be to valorize the CO2, while a closer challenge is to ensure an optimal and reliable EGR in combinations with CCUS. Okay, maybe when I was presenting you the results, you were surprised with the value or simply didn't agree with it. And this is partly why I made the tool I will talk about. To present this tool, I want you to get in the shoes of an industrial, you, who is interested in this study, maybe you, but this study doesn't reflect your own parameter, and you can't share confidential data to random student, me. So what I propose to you is to scan this QR code, choose grid data between different countries, modify each parameter following your needs and your specific power plant data, and then get your results based on it. So, okay, I think the only thing left to say is thank you for having listened to me and feel free to try the application.
Brilliant presentation. Love the energy. Thank you very much. We already have questions coming in. Brilliant. Over to you, Rainer. Thank you.
Thank you. So I think this study that you're doing is extremely important for technology development. I was just wondering, what kind of system boundaries did you use for your evaluation? I mean, just to give you an example, did you just assume the cost of creating low pressure CO2, or did you include the cost compressing it and then transporting it somewhere? And in particular, how did you do that?
Okay, the cost of compression is directly taken in the CapEx with a compression and purification unit. So three stages compression till 99.6% purified CO2 at 30 bars. And so this is the typical level of pressure and purification needed to inject it on the network, typically in Belgium. And then for the transport and storage cost, this was mainly gotten from industrial data, because at the beginning I was taking a lower transport and storage cost of CO2, but then industry, typically a member from Total Energies, told me that it was rather in the range of 40 to 50 euros per ton of CO2 transported.
Okay, so you did not assume that the CO2 would eventually have to be compressed to supercritical state?
No.
Okay, thank you.
Thank you. Alberto, over to you.
Yeah, thank you for the presentation. I think it's a very important topic on the decarbonization of the gas turbines, and also it's always nice to see some tool developed during the study. I have just a question about the capex of the carbon capture. I would like to ask how did you evaluate it, because it's the cost of carbon capture system not very available to find. It's difficult to have a defined value of the capex of this kind of system, and that are not very wide distributed at the moment.
Okay, so for the cost of carbon capture unit is mainly taken from the bare erected costs, directly taken from and gotten from Aspen Economics. But then for the EGR costs, I took the cost from a study that I can show you after if you want. And also I try to compare as much as possible to reference studies, a techno-economic study that was made. The main one I used for getting economic data, additional economic data, is from Mullen et al., but I can share you also. And then I tried to tell industry that to see if my results were correct, because I tried to manage as much as possible Aspen Economics, but it's a bit hard to manage with it. So yes.
Okay, thank you.
Brilliant, thank you. Any other questions from the jury? Perfect, thank you. Okay, thank you, John. Thank you very much for answering the questions and for your presentation. Perfect. Okay, last but not least, we've got Krzysztof Danielak from the Cranfield University. Good luck, and the time starts now.
Okay, good afternoon. My name is Krzysztof Danielak, and today I will present the findings of my research into the feasibility of using both liquid and evaporated methanol as an alternative fuel for power generation gas turbines. This research is a collaboration between Cranfield University and Uniper Technologies. Give me a second, something is not working. Okay. Methanol is a different fuel compared to methane. One of the most important differences is its lower heating value, which requires 2.5 times more methanol to be pumped than methane for the same energy output. This study focuses on a real power station equipped with Siemens gas turbine. Also, based on the future projections, as you can observe on the diagram on the right, indicates a rise in green and low carbon methanol production, highlighting its growing potential as a valuable fuel option. Previous studies also on diffusion liquid firing with kerosene have shown up to 80% reduction in NOx emissions when switching to methanol. These two aspects emphasize that methanol is a good alternative fuel and also can be used in power generation gas turbine. However, no studies have yet investigated the use of evaporated methanol in dry low NOx system. This research addresses its feasibility and combustor modifications required. In terms of methodology, initial manual calculations were performed for dual-phase methanol concept to investigate its feasibility. Then, the study focusing on three main areas: chemical kinetics to explore the benefits of methanol's chemical properties, fuel placement and mixing, and combustion analysis using CFD simulation to evaluate the use of methanol within the representative geometry of a burner. These sections aim to address the critical aspects outlined at the end of methodology 3. This is important to note that the assumptions applied in the simulations are grounded in recognized best practice, though they are not derived from detailed data. The engine features Siemens hybrid burner, dual-fuel versions capable of operating on both liquid and gaseous fuels are available. Based on this, the dual-phase approach was developed, in which the turbine starts on liquid methanol and transitions to evaporated methanol during normal operations. To address high fuel supply pressure demands associated with increased mass flow, one key design modification considered was increasing the fuel injection area. For liquid methanol, better performance was observed compared to diesel in terms of fuel evaporation. This is attributed to transfer number that is twice as high and smaller suture mean diameter, even when using enlarged injection nozzles. Evaporation and superheat of methanol can be achieved by implementing waste heat recovery, as illustrated over here. This approach can cut the fuel consumption by 5–6% comparing to liquid methanol, and also enhance mixing and potentially lower NOx emissions. Considering chemical kinetics, methanol displays higher value than methane of laminar flame speed, which increases the risk of flashback but concurrently reduces the likelihood of lean blowout. Also, based on adiabatic perfectly stirred reactor model that was used to estimate emissions under identical conditions, the results indicate that methanol produced approximately 10% lower NOx emissions than methane at the reference flame temperature. This is mainly due to chemical pathway, where early creation of steam cools down the flame. The goal of a CFD modeling was to identify injection vane modifications to accommodate methanol's higher mass flow. Two strategies were analyzed: a uniform increase in all nozzle diameters and a non-uniform increase following those two distribution patterns. In the mixing quality analysis, used the normalized equivalent ratio to evaluate fuel-air distribution. Contour plots show higher fuel presence for all methanol cases, with the unmodified configuration offering the best mixing. However, the resulting pressure losses are considered excessive. The case with uniform increase in all nozzle diameter produces a mixing pattern closest to the reference methane case, but introduces fuel-rich pockets in the low-velocity regions. Presence of a more reactive fuel in this area increases the risk of flashback. To mitigate this, a non-uniform increase in nozzle diameter was considered. This redirects the fuel towards the burner axis, eliminating rich pockets and thus reducing the flashback risk. These findings highlight the need to balance mixing quality with acceptable pressure loss. Pressure loss results also showed that increased drop is comparable to unmodified methane at 452 Kelvin. Since the burner is capable of operating with preheated fuel and such temperature conditions are used in other DLN systems, these configurations were deemed feasible and included in the combustion simulations. In the combustion modeling, all methanol-fired geometries exhibits overall flame shortening compared to methane. As you remember, this is attributed to methanol's higher flame speed, as supported by chemical kinetics. Rich fuel pockets in the corner recirculation zones observed in both methane reference case and uniform nozzle methanol case resulted in evaluated temperatures, increasing NOx emissions and the risk of overheating. Overall, the uniform nozzle configuration performed worse with higher CO and NOx levels.
Something happened. I think we lost our presenter.
Let me call him.
He's in the meeting, but I think
I see what happens. What happened? Krzysztof, do you hear us? Okay, I have to recall him.
wait a second. Yeah, we are trying to fix this issue. Let's give us a couple of minutes so we can understand what happened. I think it's technical difficulty with the Teams. Looks like the meeting has been sort of reset.
And I think we're back online. Thank you guys for sorting this out. I have to say, it's a weird feeling where you can see what's going on, but you cannot communicate. But it's okay. It was bound to happen, IT problems, but it's okay. Quick break. Everyone, just time for a quick drink, and we'll be back online soon.
I'm extremely sorry. Something happened to my Teams and it was just freezed. I don't know why.
It's okay, Krzysztof, don't worry. We've had problems this end as well, so not to worry at all.
Okay, could you please tell me at which sites there was like some kind of problems?
I think it was fine up till the end. I stopped the timer about 1 minute 30. I think you were here, but if you want to just take a nice
Here on the conclusions.
We saw until here, didn't we, Giuseppe, if I'm not
Yes,
wrong?
until here, I
Yeah.
didn't get to
Yeah.
the conclusions, no.
Yeah.
Okay, perfect. So, okay.
But, yeah, if you need some time, Chris is also okay. Don't worry, nothing happened, all is good, yeah.
Okay, if I talked already about
I would suggest exactly to go through slide 8 again, because I think this is really interesting.
Okay, so I will go once again. In the combustion modeling, all methanol-fired configuration exhibits overall flame shortening compared to methane, attributed to methanol's higher flame speed, as supported by chemical kinetics. Also, fuel-rich pockets in the corner circulation zones observed in both the methane reference and uniform nozzle case resulted in evaluated temperature, increasing NOx emissions and the risk of overheating. Overall, the uniform nozzle configuration performed worse with higher CO and NOx levels. In the unmodified case, good mixing lowered the flame temperature in the recirculation zones, reducing NOx and CO. However, CO rose slightly. In the non-uniform case, flame shortening resulted from higher fuel concentration and richer mixture in the mid-radius, producing peak temperature below those of the methane case. This configuration offers the best trade-off, with notable NOx reduction and only a slight CO increase. In the conclusion, the study showed that methanol could be considered as a potential substitute for natural gas and is worth further investigation like thermoacoustic performance or LES simulations. However, modifications to both engine burner and the fueling system are necessary to improve efficiency and make it happen possible. One of the main challenges of using methanol as a fuel is its increased flashback risk, as shown in the previous diagrams. Nevertheless, emissions benefits that can be achieved potentially, especially when using non-uniform fuel distribution and leveraging methanol's chemical properties, as you remember from perfectly stirred reactor model, can effectively lower emission and reduce flashback risk, all while maintaining an acceptable fuel supply pressure. Listed here are the main reference, and thank you very much for your attention. I would be pleased to answer any questions you might have regarding this research. I hope that this small break doesn't totally destroy the presentation.
No, absolutely not. Thank you very much. It was a great presentation. Jury, over to you for questions. Yes, Rainer?
We cannot hear you.
I was very impressed how you recovered on your presentation, so that was actually very good. On your modified combustor configuration, the problem when you have these the non-uniformity is that you probably can optimize it for one operating conditions, but did you also look into how this affects the combustor over the entire operating range?
No, because in this study, we mainly focus on the base load application, let's say, the full load application. And also, this is one of the next steps potentially in this research to check out how the combustor dynamics will work. Because, you know, I was one of the first people that were investigating DLN configuration of methanol. There was some studies in liquid firing, like it was done in Israel. Also, von Schmidt in 80s have done one of the studies. And another study was done by Siemens a year ago. And all of them were mainly looking into, is it possible? But no one of them were looking, they were looking at the fusion system, but no one was looking at in the DLN system. So yes, this is a real issue. For 100%, there need to be some kind of a combustor tuning done, and also the proper procedures of startup and shutdown.
Thank you.
Sorry, perfect. Thank you. Andrea, over to you.
Yes, I actually was, I believe, thinking a very similar question about the impact of load, in particular temperature and pressure. So in particular, what do you think it will happen in this NOx-CO trade-off when changing the flame temperature, if not done yet, based on the experience you had, how this will change with this fuel, and whether you think it could be a solution then to modify, for example, the pilot over main ratio or even the fuel temperature. Probably you didn't go through all these studies, but maybe you have already some ideas based on what you already done.
Okay, so in terms of the fuel temperature, this is based on Klimke study that was done for doing the Power Gen conference in Asia. They were recommending the temperature of alcohols, if we want to put them into the gaseous part of a combustor, to be above 15 Kelvin of evaporation temperature for particular pressures. So that was one of the, let's say, assumptions used in this study. But also in terms of NOx emissions and what you were mentioning, yes, the fuel temperature would play extreme role in terms of the adiabatic flame temperature, or whatever flame temperature, because it will rise the enthalpy. But in my potential opinion, also this earlier creation of steam can cool down. It was mentioned a few times in few studies that it can effectively cool down the hot regions. For example, in diffusion pilots, in this particular burner there was a diffusion pilot. So this creation of steam always will cool down the flame, because more or less the flame will be in the region of stoichiometric conditions. So I think this is one of the main, let's say, advantages of methanol.
Good, thank you.
Perfect. Any other questions from the jury?
Hi, Krzysztof. Sorry, guys, I can't put my hand up for some reason. But yeah,
it's okay.
Well recovered, Krzysztof, as mentioned. It's never nice to be disturbed like that, but you definitely got back on track, so well done. I'm working on some presumptions here. So I'd understand methanol would come with a standard specification with a range of properties that you'd expect. How do you anticipate that methanol at the lower end of any of those parameters of the specification would differ to the higher end of the spectrum, especially when it comes to liquid fuels? I typically expect there to be acceptable ranges for different machines. Has that been factored into your research, or how would you expect that to affect it?
Oh, okay, so we are mentioning, for example, about some contamination, about water or ethanol, something like that.
Yeah, general properties, the whole range of things you might expect.
Okay, so we were investigating, this is in ASME paper, this year ASME paper that we released from this study. Interesting fact is that water contamination cannot be properly modeled using chemical kinetics. When we compare that to experiment, they are like the trends are good, but the magnitudes are not really well performed. So this is one of the points. Another point is that it is highly depending from which material the fueling system is made of, because even the small quantity of water in two studies that I saw, one from materials and one from our journal, if there is even a small amount of water, or even, let's say, around 1%, the main problem is just corrosive cracking that is creating in the carbon steel fueling systems. So we also need to take that into account. There might be some potential benefits, for example, in terms of performance or emissions, but I haven't been investigated it so much because the overall length of the thesis was almost, I would say, extreme. So,
great. Thank you, Krzysztof.
Perfect. Thank you. So a huge thank you to all our finalists. Brilliant presentations, very clear, on time. I think our jury will have a very hard time deciding the winner. So jury, if I could ask you to go to your room and this is not punishment, but to your breakout session to make sure that you discuss all together. You've got 15 minutes and then feel free to come back and we'll have then our winner. So in the meantime, for us that we're staying in the main meeting, I am very pleased to invite our guest speaker. So we've got here today with us Simona Calenda. Simona, I trust you can use your camera and your microphone, but because of the several IT issues, maybe not. So let's have a look. Oh, yes, I can see you here. Perfect.
Yeah. Good morning.
Hi.
Good morning, everyone.
So I have a quick question. How do I get to that room? I don't have any button for that.
Yeah, Nico will try to put us in that room, Rainer. Just wait a
Okay.
couple of seconds.
Okay,
Perfect, thank you.
thanks.
Hi, Simona. Such a great honor to have you here. So for everyone who doesn't know, Simona is the winner of the last year Brian Pitt Excellence Award. Thank you very much for joining us. Would you like to tell us a little bit more about yourself, your role, just so our guest can get you know better?
Yeah. Good morning, everyone. Thank you for inviting me in this final. I'm Simona Calenda. I'm an energy engineer. I graduated about a year and a half ago, and I've been working for a year in the asset management and O&M team at Renovit, which is a small company that is part of the SNAM group. Our core business consists of investing in the construction of cogeneration and photovoltaic power plants for industrial clients. We typically sign long-term agreements where the clients commit to purchasing electricity and thermal energy from our power plants for the entire duration of the contract. My team is involved in the last part of the value chain. We handle with the operation, the monitoring, and the performance of optimizations of the power plants, which are already in operation.
Brilliant. I think it was really nice to catch up earlier in the week and find out that we actually have a very similar job.
Yeah,
and
true.
just in different countries. And it's always nice to find fellow engineers and share the struggles and everything like that. Also one of the great value. Yes, sorry, Nico. Yeah.
Thanks. Rainer, I think you should have received the invitation to join the room, the breakout room. Can you confirm?
No, I don't see anything.
Is there like a small button?
Okay. How
on
about
the-
now?
Hang on.
You should receive the notification on the screen.
That should be under notifications, and I don't see anything there.
Okay, let me check.
I mean, I can try to call in again, leave and call in again.
Yeah, please. Yeah, please.
Okay.
Why? Thank you.
I'll try that.
Thank you.
Yeah, thank you.
Sorry, of course, there's always IT, but IT being IT. But yes, sorry, Simon. I was gonna. How did you find your transition from university to industry?
The transition from the university to the industry is definitely a big change. I think that it's like this for everyone. And because at university, the focus is more on theoretical things and on kind of problem solving that is in a more academic shape. But when you start working, you realize that how much is important to apply what you learn theoretically in the real life situations, especially sometimes also under time constraint and while being part of a team. Because when you are at university, you are alone, you manage your time, but when you start working, you become part of a big chain in which you are just a small part of it. And so you have to understand where you are and how you can contribute in a good way also to the work of the other people. And so it took time to adjust to the pace of the situation on the work world. And I think that is quite common to think at first, as well as happened to me. I thought at the beginning that the work world would be simpler with respect to what I studied at university. And sometimes I also thought that what I studied would be useless for my career. But by the time this feeling got over, and then I realized that I started developing many other skills, especially human one. I mean, I think that I'm developing the importance of being able of dealing with people, working with clients, and also managing the real life situations. And for certain, one of the things that I appreciate most of my work is the possibility of visiting the power plants, because I think that is the best way to understand what I studied some years ago just theoretically, but now I have the possibility to visit the power plants and to see what I studied in real life application.
It's true. I also love going to the power plants, especially after a full week in meetings in the office, and you're like, okay,
Yeah.
let me go to the station, let me get my hands dirty a little bit. Yeah. See what the world is really like. Yeah, I remember when I transitioned from uni to university, it was just like, what have I studied 4 years for? Like, and and you're just like, but then everything makes sense somehow.
Yeah, it's quite similar.
Yeah, absolutely. So we've got all our finalists here with us and listening, of course, to us. And what, thinking back of your experience on the Brian Pitt Excellence Award, how do you think this has shaped you in your career?
Yeah. I took part to the last edition of the Brian Pitt without any big expectation. I just thought that it was a great competition and I would like the idea of being part of it. And winning was totally unexpected to me. And it was a real, first of all, it was a real recognition for the hard work of the previous month. And then it was a real great occasion to take part to the conference in Stuttgart, which I found really interesting. It was the first time that I joined an ETN conference, and I think that it's really interesting for many reasons. I had the possibility to meet many people who share with me their past experiences, their stories. So it was really enriching for me. And I also had the possibility to understand how many opportunities are in our field. And so to understand what I would like to do in the future and in my present career. And so I definitely suggest to take part to this competition also to future students. So apply to this competition and take part on it.
Yeah, absolutely. I think it's a brilliant competition, and I'm glad of all the benefits, and also I think it's a great way to meet people and to share thoughts, and obviously the brilliant work has been done. But because our winners also will be presenting maybe at the next big conference. So I think from today I've seen brilliant presentations, of course, but I can understand there's probably a bit difference when you've got a big audience in front of you. What was it like for you? Do you have any tips for our audience to be able to master those presentation skills and that anxiety? And
I have to admit that I was a bit nervous about the idea of presenting in front of such many this big audience, especially made by experts of the industry sector. But so I felt a bit nervous the day of the conference, but the welcome was great, so no worry. And it was a really inspiring experience because stepping out of my comfort zone was a really positive experience to me. And I think that it was really rewarding when you understand that people appreciate your work. And so I think that what will come is just good things for you. And so my advice is just to don't be afraid about the situation, to live the situation positively, and to enjoy, to take the chance of connect with people, because I think that it's also a big chance to build a great networking and enjoy the situation, the experience, and good luck for the future winner.
Yeah. I'm excited also to see you as our winner indeed. I think our jury is deciding as we speak. By the way, if anyone from the audience have got any questions for Simona, feel free to put them in the chat, because of course we've got a great guest speaker with us. So, yeah. I don't know, Simona, if you wanted to share a little bit more about maybe your research from last year. Your research in general, but like that made you win last year.
Yes, for sure. My research was about the flexibility of combined cycle with carbon capture and storage systems, especially the small one. So the one in the utility scales. We studied the flexibility with different assets. We compared many solutions and we discovered which one was the best. And we understood that the best solution was the best solution was the one with the compressor upside of the downstream, since it guarantees the maximum flexibility. That was the main purpose of our study. And if you want to know more about it, feel free to reach out with me. And I don't know.
Yeah, Simona, of course, she's brilliant at her job, also great research. And thank you very much for being with us here today, for sharing your pills of knowledge, your tips. I'm sure people have really benefited. And if I could maybe ask our finalists to come back online, try and share your videos back on. I think it's been an intense session with some also IT problems. But I think so for Thomas it's not working yet, so we'll try and figure that out. And I think we've had some setbacks, but it always happens. It's life, real life in this meeting. And I think
like work life right? Is the same.
It's true. We're just preparing you for what industry is like. Yeah,
that's true.
Yeah. Nico, can I ask you to help us out for the camera, please? Because I've enabled them, but I think,
Thank you a lot for inviting me.
It was an absolute pleasure, Simon. Yeah.
Thank you.
Absolutely. Thank you very much.
And good luck for all the finalists.
Thank you.
Bye.
Bye, Simona. Bye. So also in the meantime, while we wait for our jury, I think so Nico has shared a survey. It will be very appreciated if you could please fill it in, share your views. That will really help us out in doing better next time. But also, just see if you enjoyed our meeting. So let's see if Thomas now can share. Anyways, to our finalists, how are you feeling? Any thoughts? Did you also enjoy the presentation of the others? Because I think that was great knowledge sharing. I definitely learned a lot. Good. Yeah.
Yeah, that was good. I learned a lot personally from different presentations, and thank you to all the finalists for having shared this to us. And yes, that was really good.
Brilliant. I'm glad. So I can see the jury back in. Giuseppe, all okay? Andrea, Daniel, Alberto, Rainer?
Yep, all good.
Do we have a decision? So who's in
Andrea
charge?
will present it.
Okay, perfect.
Andrea Ansani from Ansaldo Energia will present the results of the decision.
Perfect. Andrea, the floor is yours. I say roll of drums and yeah.
Okay, thank you very much. And indeed, it was a pleasure to follow all these presentations. And yeah, it seems I have the duty and the honor to announce the winner. I can share that it was a tough race because all presentations and all the works were really good, high level, well presented. And we had several assessment criteria, and actually the scores were all very high. And at the end, though, one winner is clear, and I can announce this is Krzysztof Danielak with the presentation on the methanol. So congratulations,
Well done.
And definitely well deserved.
Yeah, I think our winner and our finalists, they all deserved a big applause, of course, from everyone. Thank you very much, jury. Krzysztof, now you can go and enjoy and celebrate. And are you happy? I know it's silly questions, but
for 100%, even with with having those problems, I think this is like a little bit. I was thinking that it's not gonna happen, but this is a really good point of view. And also potentially today I'm gonna just grab some wine and probably I'm gonna just party the whole day.
And forget about the research. Yeah.
Yes, exactly.
Brilliant. I also want to say our finalists were absolutely brilliant. It was a pleasure to listen to all of your presentations, and I can see all the congratulations coming in. And I really hope you can all make it to the IGTC in October in Brussels. It would be a pleasure to meet you in real life and to discuss some more your papers and your future and everything, all the good things that are due to come, as we learned from Simona that there's a lot of opening of doors and hopefully joining the ETN and having a brilliant step into either more education or industry. For myself personally, I wanted to, it's been a tough meeting at times, but I really want to say thank you to Giuseppe and to Nico for really have helped me out here with all the IT and all the things in the background. Also, thank you to the jury. Thank you for your engagement and for your decision making and for everything. Giuseppe, would you like to add anything else from ETN?
Was a good. I read the papers, as I said, so I really know what the discussion was about, but it was a pleasure to listen to all. And listen, the presentation is a great opportunity to practice, but also for us, great opportunity to learn. So I must say that all the finalists will be invited to submit a poster to the GTC, so they can present the results to even wider audience at a conference. And the paper from Krzysztof will be sent to a conference advisory board. And if approved, you might have the possibility to be included in a technical program, but this doesn't depend on us anymore. It depends on the conference advisory board. So good luck with that. Hope you make it, because the work is surely relevant to the industry. And nothing. That was a great meeting. Thank you very much all to the participant and to the jury and to